Good afternoon, everyone. So we learned a few fundamentals and like the significance and just like we how the GA works. So we are basically have a picture that how it works. Good afternoon. So let's try to understand with a particular example each and every step of the like how we can use genetic algorithm. So we had a very fundamental problem which we already discussed earlier, that summation over I equals to 1 to n Ci Pgi, and subject to that our summation of Pgi was equals to some power demand plus losses, and losses we defined some function. Okay, so losses has been defined with certain function, and our PGI is less than equals to whatever is PGI max and then PGI min. Okay, so this is what we the problem we had. So let's assume that there are n equals to 3. So we have 3 generators. Certain post function is there, and let's say like PG1 is less than 600 and 150. PG2 is 400 and 100. Let's say 50 and 200 is PG3. Now, before creating a population for a genetic algorithm, we have to look for like how much bits we need for each and every variable. So we have variables are basically are P1, P2, and P3. So this is a variable, and I can say this will be the my chromosome as well. Okay, so let's say how many bits will be needed to convert this 600 into the binary. So let's say 600. So how many bits are going to we are going to will need basically to convert this into binary. So like I also did with the calculator here, and it's a 4 5 6, and so 8 bits we'll need to convert like this 600 into binary. So there will be 8 bits we are going to need. Now if I only use 8 number of bits, then we will get an integer kind of solution. The PG1 will have value of like let's say 300, 301, 302, and the fractional elements will not be basically there. So we need at least let's say if we need 3 like decimal places, and up to like accuracy up to 3 decimal places or 2 decimal places, how many bits will be needed? Can somebody Google it and let me know? Like up to 2 decimal places, how many bits we need? So for 2 decimal places, the maximum value can be like 0.99, and if you convert that 0.929 into binary, it's basically infinitely very long string. Okay, so it will keep on basically increasing. So let's say we take 10 bits for our integer part, like to represent up to 600, and then we can have like 0.99 and like to represent, that is the maximum value, up to two decimal place. It will need a very long basically script. So let's say we take six more bits for to represent the decimal part. So a single chromosome size, so like the chromosome size will be 10 bits to represent the like the real part. Then let's say I use 10 bits for the subsequent um, parts in the decimal. Now, can you provide me like for 400, how many bits is needed? And then how many is needed for 200? I'm waiting for your answer. Okay, so thank you. It's 9 for 400 and 8 for 200. So I will assume like I will keep the same number of bits. So let's say 9 bits we need for P2. Then 10 bits we'll need for the fractional part, and then 8 bits for P3, and 10 bits for the fractional part. So this will be the overall size. And we, like it's only one, like 9 bits and 8 bits are there. So just to keep it uniform, I can also, like instead of 9 I can keep 10, and I can keep 10. But for this particular problem, I can keep, like to represent these P1, P2, P3, I will need 10 bits for the both like fractional part as well as the real part. Okay, now if our problem size is very much high, this like how many bits you need will play a very crucial role. So like this 600, 400, 200, these are the, like right values. So I would prefer that, okay, at least 10 bits are needed for them. And but like up to how much accuracy you want the answer, that will be decided by the fractional part. Okay, so for that, how many bits you need is a big question mark. But yes, let's say for this particular problem we can keep at, like 10 bits. Sometimes we can go, like number of variables are very much large, then this chromosome size will be too much. So sir, for decimal place, if we take 0 to 99 with the power of 2 or 7 bits enough for decimal place. So there are yes, Satya has placed a comment that for 99, if we like assume that certain bits are there for like before fraction, and certain like after the decimal, uh, only 99 is there, so we can use 7 bits are enough. So it's a way how you decode the binary. If I simply search, let's say, like if you simply search like convert 1.99 into binary, it will give you 1 will be 1 directly. Okay, but 0.99 is infinitely long series. Okay, and like you will end up 20-30 bits. Okay, so the thing is like how you decode the binary into the real values, because we are going to need the real values to calculate the objective function value. So it's up to you. Okay, so if I directly use like some inbuilt function convert binary into decimal, then I will need let's say, okay, let me decide like 20 bits are reserved for the P1, 20 bits for P2, and 20 bits for P3. And if I'm like trying to decode with the help of MATLAB, what I will do is is there some function binary to decimal in MATLAB? I have no idea, but there should be some function, right? Binary to decimal in MATLAB. Yeah, bin2des is the function. I was hoping it should be there. So I will simply put bin2des, and let's say it is population, the very first chromosome, and 1 to 20. This will be the value of P1 simply. Okay, that whatever is the population in that the very first chromosome, and the initial first 20 bits are reserved for P1. So will directly use that value bin to deck, and I can obtain the P1 value. Okay, here this is part one. Like you can directly convert that like the value of P1 as suggested by Satya as well. Like instead of considering this as a entire chromosome series, so I will place a point here as well, and I will give that information. And so I can also have a 10 bits for, let's say, uh, before decimal part, and 7 bits for the next decimal parts, and so on for P2 and P3 as well. Here what I can do is I can convert bin to des, uh, like whatever is our population and the first chromosome, and let's say 1 to 10. So that will give me some value A, and then I will use the same command, and then 1 and 11 to 17. Okay, this will give me some B part, and then I can use that. Okay, if this is been basically a decimal value, and we know that this value is only up to uh, so 7 bits. How, what is the maximum number a 7 bits can represent? Anyone? 1, 2, 3, 4, 5, 6. So yes, thank you, Satya. It's a 128. So let's say if these bits which should represent 0.99 are the after decimal place, and if they all are equals to 1, I will get 128. Okay, so it is more than 99. So in that case, it is very difficult for me to like I have to apply some conditions as well here. So once I obtain this value, then I have to apply some conditions, that if this value is like b, if b is more than 99, then keep b equals to 99. Okay, if it is less than, then we can get the value whatever we have so far. So this condition we have to apply, and once it has been applied, then I can say that the P1 is nothing but A plus B by 100. So this is how I can decode it. So for first part is like we have to look how we are going to decode our binary bits. Based upon that, we will build our chromosome as well. Okay, so there are multiple ways of doing it. It's a GA will not restrict you that how you should do. You can like literally convert this. So like we have a generator of 600 megawatts, so I can easily convert like 599.9999 and convert that into binary and see how many bits it needs, and you can place that. Okay, these many bits I'm going to use for my chromosome size for variable P1. Okay, so let's just to keep it very simple, let's say that we are using 10 plus 10 bits for each segment. Okay, and then you know how to basically decode it. So that decoding process is uh, like it's very you have to place a point as well, otherwise it will not be able to so you have to convert to this chromosome size, it's 0 and 1, and no point is basically available in between. So you have to convert that entire matrix into a string, and a string where a decimal will also be placed, and then we can use binary to decimal to get a real value with respect to that. Otherwise these 10 bits will give you a very high value, like 7 bits are giving 128, right? So 8 will give you like 128 into 2, and so on. You can keep on multiplying with the 2, you will get like very high value as compared to 0.99 which we want to represent it. So it's a uh, your decision, like how many bits you need, how you handle the data, and how much large is the problem. Based upon that we will decide that okay, these many bits we are going to need, or like how to handle this particular problem. So first part is like how we are going to decode each and every binary into the real values. So we discussed that the very first step is initialization, creating or basically initializing the population. So what I can do is I can randomly generate some population. That is also fine. So you can there are different functions in MATLAB which generate 0 and 1. Okay, so you can basically randomly create the population. Let's say this is there any command to create the random values in MATLAB? Thank you. But this will give me the values like between 0 and 1. I have to create randomly generate binary numbers. Yes, rand integer is we can convert basically integer values between any range. So randomly generate. So binary numbers I have to generate because it will be easier for me. Any idea? So let's say we only know this rand integer. So how we can use this one, or we can write our own code as well, like to create a particular population. So yes, with the help of ceiling, or like taking the like either yes, ceiling will be creating, like if it is more than 0.5 then it will go up to 1, and if other is less than 0.5 then it will put it on the ceiling. Is I think roof and floor was the like to either keep it move is it upwards, or otherwise it is below. And yes, so we can use, there are multiple functions. Thank you for your inputs, like we can create random n numbers, and we can create random integers, and then we can create like use the ceiling function as well if we are using random values. So if I use some random integer values, okay, so let me show you my entire screen. Stop, share entire screen, and MATLAB. Okay, so it's a random integer, and this is how it will create the certain basically matrix. So so there is one more input from you guys that we have some inbuilt GA as well. So yes, we have inbuilt GA function in MATLAB. We can use that one. And for like this economic load dispatch problem, I would prefer that one because it's a very simple problem. But if we are trying to write down like our own values, or so let's say if I use this particular function where I provide 1 comma 3 comma 4, let's see how it generates. So okay, it is creating like 1 and 2 only. It does not produce 0. So I can use some of you mentioned ceiling and then random number. Okay, wait. Ceiling random, where I'm making a mistake. Okay, so ceiling is creating undefined function. Thank you. So ceiling is giving me like higher value. So what else we can have? So floor and seal is basically giving me the higher value. Uh, what else we can use? Yeah, I used this one. It is giving me one. Any other suggestion? Round we should use. Okay, so this will give me the perfectly like I will round it up to the values. Let's say 5 comma 10, and I will get a matrix like this. Okay, so this is how I can create a population. So like we had this one, and I will use like the population is equals to round. Then you give me a function that I can use this one, and population size I will provide. So whatever is the like population size comma, I will use chromosome size. Okay, so this will create me the population. I think we are all on board. And let's say if I'm going to create uh, 10 chromosomes, and the chromosome size we have defined earlier that 10 bits is needed for each variable. So 20 and into 360 bits will be needed. So I will provide this as a 60. Okay. So 10 comma 60 I will provide, and that will create the initial population. Uh, if you have any doubts regarding this, like how we create a population, so like if you are trying to write down everything from the scratch, this is how we create the population, first of all. So Once we have initialized the population, the second step is basically decoding it. Okay, so we have to decode this entire population into real values of P1, P2, and P3. So depending upon, like, I have discussed you like two different approach there. Like, we can convert certain part into a string, place a dot in between, and then use binary to decimal. Then we will get some binary value which is close to like 0.99, or like only on like the fractional part will be there. Otherwise, we can use like the second approach where only 7 bits we used, and then if it was more than 99, then we can fix it to 99 and like divide by 100 and add it to that. So we decode the chromosomes and obtain real values. Okay, so we will based upon the same logic by which we have visualized our initial population and come up with the chromosome size. We will decode the chromosome and obtain the real values of each population. Okay, so here we have created a population of 10, and then some chromosome size. Based upon that, we will decode it to the real values. Once we have decoded it to the real value, you can put those values in this objective function. But now the issue is how to handle this equality constraint. Okay, that is always a issue. Like, we have to handle this equality constraint that if the PD plus PLO should equals to PGI. As we have initialized the population, we will get some P1, P2, P3 values. And if I put those P1, P2, P3 values in the this loss function, I will get certain losses. Okay, and it is quite obvious that the summation of that generation will never be equals to the demand plus losses. It will be something else. Okay, so we will never get exactly, like, we will never be able to satisfy this particular uh, function. So how to handle this kind of situation? Okay, it is again a issue. So one way of doing is like, so the thing is, like, you have to develop an algorithm, and how you handle different constraints and different inequality and equality conditions. It's again like different ways of solving is possible. So one way of doing is like, I can use the like P1, P2, P3 values, and just initialize P1 and P2. The P3 will be PD minus P1, P2. I can use that approach as well, like reduced the number of variables, because I know that this equality constraint is there. And once I have identified P1 and P2, I can calculate the P3 value. But this P loss will create a problem in that situation. So what I can do is I can put the P1, P2 in the P loss and keep plotting the P3 and solve this particular equation and obtain the P3 value. That approach is also feasible. Okay. So another approach is let's not do any of these things, and we have P1, P2, P3. So it's randomly generated values. Okay. It is quite obvious that they are not going to support this particular equality constraint. Okay. If they are not able to support this particular equality constraint, we can create the fitness of that particular chromosome 0. If we are doing so, our entire population fitness will be 0, and we will not get any solution. So generally, in GA, what we do is we create the like all of these conditions are placed in the objective function with the penalty terms. So everything should be placed in the objective function and some sort of penalties. So if you are deviating this condition, okay, or if you are deviating the maximum limit or minimum limit, a penalty will be imposed in the function. And as the objective function is minimization, that penalty will lead the objective function value to higher, and it will reduce the fitness of that particular chromosome. Okay, so everything can be placed in the objective function and with the penalty term. So I can put it like, this entire objective function is basically summation of ci pgi plus some lambda pd plus plos minus summation of pgi plus some mu and pgi minus pgi max and plus some another mu, and it is minus pgi plus pgi min. Okay, so this is how we can satisfy it. But if again the issue is, if I try to solve this one, this solution will be like, as a penalty it has been placed, so these values, the first power balance equation will be satisfied just to get the optimization minimum. This condition will be there, and like, if it is zero, then only we will have the best fitness. Otherwise, um, the cost will be more, okay, because of this particular first penalty term. Second penalty term is, uh, if pgi is less than the pgi max, so the entire term will be negative, and this derives this particular entire objective function, and like that, okay, it is creating a negative value in the penalty term. If it is creating a negative value in the objective function, then uh, like the optimization will try to reduce the value of pgi, or even ga will also do the same thing, like it will reduce the value of pgi to very low value. Second is, if pgi is basically like if you use the minimum condition, uh, it will be negative if pgi is more than the pg min. Okay, so so it depends that how, what is the value you are using for these penalty term, and how they are going to affect our solution. So this mu and lambda values will affect it too much. Okay, so it's like mu1 and mu2 with respect to both the upper and lower limits. So this is like, one way of doing it. Another way of doing it, you just don't consider these two. Okay, do not consider the upper and lower limit, and we will see about them, that how we can handle them. But this equality constraint we have to consider, because we have to satisfy this constraint. So I can simply put or write down the Lagrangian function which we have discussed earlier, and use that as a objective function. So once I have decoded all the randomly generated 0 and 1s into the real values, I will obtain or calculate the function value. Okay, and that function value will be your summation of ci pgi plus certain lambda, and then we have this pd plus plos minus summation of pi. Here the thing is, like earlier, this plos we have to calculate separately and all. In this particular case, as different p1, p2, p3 are already there in the population, we will simply put the values here, and we will get this particular function value, and then we can calculate the fitness of each population. So that will be, let's say, one some k upon fx, whatever is the function value. Let's say this was our fx, so we will get a fitness value, and so this is how we can calculate the fitness. So that is part number 2. Any doubts so far? No? There should be some doubts. Let's say, so I'm using 10 bits for P1, P2, and P3. And let's say all the bits in this first 10 bits are 1. Then it will be definitely more than 600. Okay. So while decoding, if a limit is being hit, So it has been randomly created values P1, P2, P3, right? And they can easily hit the maximum and minimum limit. And I gave you that, okay, do not consider this particular part. So in that case, there are again two other ways of doing it. Either you fix that value to the particular limit. Okay. So before doing it, we have to basically check for the limits. So obtain the real values and then check for limits. Okay. So let's say the population 1 and the values were, let's assume 500, 300 and 100. So all are in range. Okay, so that is for population 1. Then for population number 2, let's say this was coming 700, 300 and 120. So the generator 1 is more than the P max of the first generator. Now what I can do? Anyone who's familiar with GA or who has some idea how we can handle this particular situation for the GA? Mutate? No. So the first population, I can simply calculate the fitness one, which is 1 upon, let's say, whatever was my Lagrangian function where pi and lambda I was there. So this above overall function, it was basically the Lagrangian function with the pgi and lambda. Okay, so I will use that function here and I can calculate the fitness one. Then there are, whenever this kind of situation happens, we basically can have two ways of solving it. One is keep P1 equals to P1 max, okay, and respective change in population as well. Okay, so population will have let's say 700. So we will keep it to 600, and whatever is the binary equivalent of 600, we will replace that here in the population. Okay, we can do that. That's the same approach by which we solved earlier. So we know that that approach is effective, so we can use that one. Another is so expected change in the population, and then further we can calculate. So once it has been like up to 600, we can calculate the fitness function for the second as well, whatever is the Lagrangian function for this particular population. Another thing is, whenever this has been set, I can simply keep fitness equals to 0. That is also possible. So I have placed that, okay, the fitness of this particular chromosome should be 0, that it is not satisfying my limits. Okay, so both the approach we can use. So if I decide that this fitness is 0, it means this chromosome will not have any role to play in the subsequent iterations, and it will be discouraged to use this chromosome. Okay, because its fitness is very low, it's 0, so we can define it 0 as well. So both the approaches are there. Whenever a limit is hit for a particular variable, we will try to either we fix to that particular limit. So and otherwise, basically, we can keep the fitness equals to 0 for that particular entire population. It's not with respect to variable. For the entire population, we keep the fitness equals to 0. So is this clear so far? Okay, so once we have obtained the fitness, so the third step was, I think, we discussed earlier, the third step should be uh, there are different variants of GA. Sometimes we use elite chromosome to be carry forwarded. Sometimes, we do not use elite chromosome. So all type of, multiple ways or multiple, basically variants of GA is there. Let's say we use elite chromosomes. So we will perform that of the best chromosomes should be carried forwarded to the next, basically population. So generally we basically perform elitism. Okay, and generally the probability for elitism is roughly around 2 to 5%. Okay, so we keep 2 to 5% probability, and 2% is basically, let's say if there are 100 population, best two chromosomes will be basically part of a transfer to child population or the new population. Okay, so whatever, let's say if it is two, then we will keep the two population to the next, basically like the new population as well. So we'll copy those two as it is. That okay, these are our best chromosomes, and we will try to have them in the next population as well. Then fourth is uh, selection. So this is also, like part of selection process. Selection 4, elitism, and then we will perform a selection process. Selection, there are multiple ways, like how to select the chromosome. So generally, what we do is we can sort uh, all population with respect to the fitness value. Okay, so we can sort them with the fitness value, and so best fitted will go up, and the lowest fitness will go down, and then we can select certain, like population, or like for certain fitness value. Let's say above 70% or 80%, we can select that okay, these chromosomes will be used for the crossover. Or what we can do is we can have different basically ways for the selection. So the one method is roulette wheel. Okay, so another is rank. There are tournament as well. So different methods are there basically. Now wait. So let's talk about these methods. So first is roulette wheel. Okay, I gave you a very simple selection process that showed all the population with respect to function value, and let's say keep X% for reproduction. That is one way of doing it, like straightforward. Yes. So one is like, we have to select certain population, and we will select the fittest chromosomes and use those chromosomes for the reproduction process. Okay. So there are multiple ways of selecting chromosomes. So like the entire GA works like first of all we have to create the initialized population, then decode and obtain the fitness value. Once fitness value has been obtained, the next part is uh, if we are using elitism as well. So we for first we will do elitism. Second is we will do crossover, and third part is mutation. So these are like crossover and mutation are always part of the genetic algorithm. In if we are looking at the like elitism GA, we also perform elite like chromosomes should be carry forwarded. So the first part we have discussed. Second is selecting. So one way is a straightforward way is short everything, and let's say keep 80% of the top chromosome be available for the reproduction, or you can keep like all 100% of the chromosome for the reproduction. So it's again up to the user, the way we are basically looking at the problem and the way we want to get a solution. And all of these decisions will affect the overall result. Sometimes the convergence will be faster, sometimes it is lesser, okay, slower basically. So in roulette wheel as well, I can apply the roulette wheel for the only 80% of the chromosome which have best fitness, or I can apply for the 100% of the chromosome. So for what is a roulette wheel, let's talk about that. So what we do is we will calculate a probability first of all. So here, so we have obtained a fitness function for all the chromosomes. So I will calculate the total fitness, which is I equals to 1 to population size, and I will sum up the all entire fitness. Then after that, I can calculate some probability of ith uh, po- population or ith chromosome, and that will be equals to like whatever is the fitness divided by the total uh, fitness. And once I have obtained this one, I can calculate the cumulative probabilities, and that will be, let's say, cumulative probability of I. That will be, I think, equals to J equals to 1 to I and probability of I. Okay, and I have to, I think, add J. So it is okay. How to calculate this one? Cumulative probability, it's 0 plus 1 plus 2. How we can calculate the cumulative probability? It is basically like adding up to 1, then 2. So summation of probability over J. Okay, so we will add them up. Okay, so let's assume certain population, let's say chromosome 1, chromosome 2, chromosome 3. I'm just randomly giving some values. Okay, some fitness function is given, let's say at 10, 5, 6. So total is how much? The total S value will be equals to S value will be equals to summation of these, and that will be 21. Then I can calculate the individual probability. Individual probability will be 10 by 21, 5 by 21, and 6 by 21. Then I can calculate the cumulative probability CPI, and that will be 10 by 21, then 10 by 21 plus 5 by 21, and then 10 by 21 plus 5 by 21 plus 6 by 21. Okay, so this is we can calculate. So this will be equals to 1 itself. Okay, so we have calculated this one. Then we will create a roulette wheel. So let's say we start from this particular part. What is 10 by 21? Roughly around 50. So I would say this is 10 by 21. Then we have plus 5 by 21. So that will be this. So this is basically the overall probability is plus 5 by 21. And then last is basically the 6 by 21, or the overall is like what this is 10 by 21. This entire probability is the CP2, and then the last is cumulative probability of up to this part is CP3, which is equals to 1. This is clear. So this is a wheel we create, and then we randomly generate a value. So like randomly generate a value between 0 and 1 again. Once we have generated, so it's basically like rolling the wheel. So this is a wheel, and we will roll the wheel. Let's say the value is 0.4. So 0.4 is somewhere here. So the wheel will point in this particular section, and we will use this as a parent. Then we will again roll the wheel with another random value. Okay, so we will randomly generate another value between 0 and 1 and choose the second parent. So this is how we will basically, with from the existing population, we will select multiple parents. So once we have selected two parents, we perform crossover. Is there any doubts in this particular philosophy? So we roll the dice, which means randomly generating a value between 0 and 1. What happens here is, uh, let's say the value is very small. Okay, so if the fitness value is very small as compared to the total fitness, so let's take another example. Let's say some chromosome 1 has a value of 100, chromosome 2 has a value of 50, or let's say not 25. Chromosome 3 has a value of, let's assume again, let's say 50, and chromosome 4 has a value of 10. In this particular example, I can basically calculate that total sum that will be equals to, let's make it 50, 15. So 120, 170, 80, 190. Okay, so it is 190 is the total summation by which I can calculate. So this is my fitness. I can calculate the probabilities. So it is 100 by 190, 250 by 190, 50 by 190, and 15 by 190. And then I can calculate the cumulative probabilities as well, respectively. If I draw the wagon wheel for this one, so it will be like a circle, and let's start from the 0. Let's say this point is 0. So 10 by 190 is roughly around 50%. Okay, and so this will be 100 by 190. Then this is 25 by 190, and then we have 50 by 190. So it's like 25, uh, 50 by 190, half of the previous, and then 15 by 190. So the probabilities will be like so I'm just using, let's say this probability is 0.5. This probability will be 0.0, or basically 125. This is roughly around 0.25, and this will be, let's assume, whatever is the remaining. So how much is the left basically? 1.25 itself, right? Okay, this is even note it is 0.5. So okay, so some values will be there. Now if I generate a random value between 0 and 1, it's most likely that the value is, like, let's say, the chance of value is being less than 0.5. It will, so the value will be uniformly distributed. So it will generate, it can generate many values between 0 and 1. But getting a value which is less than zero point 0.5, so let's say this is, if this is 0.5, is 50% chance. So 50% time the first chromosome, or the first chromosome, will be selected as a parent. But if you look at like this particular node and this particular, like, second and fourth chromosome, they have very less chance to be selected as a parent. So it's basically survival of fittest, we can say. And they will have very less chance to be selected in the uh, selection process. So this is how we roll a randomly generated value. We get one parent, we again randomly generate a value, and based upon where that value lies, we get the second parent. And once two parents are there, we perform the crossover operation. Okay, so this is the roulette wheel method. Another is rank based method as well. In the rank based method, it's similar to roulette wheel, but not exactly a roulette wheel. Okay, so let me consider, like, the same example. So C1 is 100, this was, I think, 25, 50, and C4 was 50. Okay, so what we will do is we will give them a rank based upon the their probability. So we will do, like, sorting from highest fitness to lowest fitness, and then provide a rank. And I can directly provide that this is the rank 1, this is the rank 2, this is 3, and this is rank 4. Based upon that, I will do a summation of the ranks. Okay, so it is basically how much, 3, 4, 4, 8, and 10 is the total sum. So I can calculate the probability of ith. It is 0.1. uh, Basically, okay, we have to give them a opposite rank. So this will give the fourth rank, and this will get third, 2, and 1. So the probability here will be 0.1 divided by 10. This will have probability 0.4, this will have 0.3, and this will have 0.2 probabilities. Okay, and the total summation will be 1. Okay, now if I calculate the like, cumulative probability, it is 0.4, then it is 0.6, then it is 0.9, and then 1. So the roulette wheel I will draw with the rank method. I will again draw a roulette wheel, let's say. So instead of 50%, now it is 40% only. So it is 0.4, then 0.6, so roughly around here. So this is 0.2, and this is 0.6, this is 0.4, and then we have 30%. So this is, wait, we have to make them in the order. Okay, okay, okay. Other way it is also fine. 0.3 and 0.9, and then this is 0.1, and this is 1 and 0. Okay, so you can see here, like, the first chromosome which has highest fitness, and here as well it has highest fitness and the rank, top rank. Here it was, the probability was 0.5, 50% probability. Now the probability is less. Okay, so if there are both of these two methods. Again, I will randomly generate some value, select one parent, randomly generate some value, and based upon those values from this particular wheel, we can select the second parent, and then we perform the crossover. The difference between these two methods is uh, the very first method is basically depends upon the exact fitness value, and if one chromosome has a very large fitness value as compared to the other chromosome, that chromosome will always dominate. So you can see here, this chromosome will always dominate relatively, the fourth one and the third one, because the area given to them is very less. But if we use the rank one, the probabilities will remain always same. It will be always for this particular case, four bus system or four population size, the probabilities will remain always same. It is always like zero point 0.4, zero point 0.2, 0.3, zero point 0.2, and zero point 0.1. Okay, so these will be the probabilities. If there are 5 chromosomes, then we will have a additional 5 rank as well. So the total will be 15, and the probabilities will be 5 by 15, 4 by 15, 3 by 15. So over the iterations, these probabilities will remain same, but the chromosome number will change. That okay, maybe some other chromosome becomes the highest rank, and the rank will basically vary over the iterations. But here if a chromosome has very high fitness, it will never dominate the entire solution, and it will have the the same number of chance to get selected. If fitness dominates everything, it will have higher chance to be selected each and every time for the reproduction. Okay, so this is how the rank method is like bit better as compared to the our classical roulette wheel. Another method is tournament as well. Okay, so tournament selection. In tournament selection, we basically randomly pick n chromosomes and keep best fitness chromosome as parent. Okay, so let's say I have a population of 100. I will randomly pick any chromosome, or randomly pick n number of chromosomes. So this n is very crucial here, like how many chromosomes you are going to pick. Let's say if I pick 2 chromosomes out of 100, and then I will compare those two chromosomes. Whoever has the better fitness or the more fitness will be selected as a parent. Then again, out of 100, I will again pick uh, 2 chromosomes, and then see whether they are basically how much whichever has the highest fitness, I will keep that chromosome as a parent, and this is how I can select 2 parents, and then I perform the crossover over them. Can you tell me what will happen if this, let's say n is the uh, number of chromosome for the tournament selection, if this n is equals to the population size, what will happen in this particular case? That let's say 100 chromosomes are there, and if I randomly pick, okay, let's say if I pick randomly 3 chromosomes, out of those three, whichever chromosome is the best one with respect to the fitness, I will keep that chromosome as a parent. Then if I again choose 3 chromosomes, if NT value is 3, and whichever has the better fitness, I will keep that particular chromosome as a parent. What will happen if this NT is equals to population size? You can raise your hand if you want to answer verbally. Ankit is saying process will never end. Dr. Nishant, do you want to answer? Ujjwal? So let me tell you, it's not the case that process will never end. Process will end instantly. The thing is, just look at like how our stopping criteria works. Stopping criteria is like, whenever we are not able to create a new population, and if the difference between the fitness values of the best, let's say, chromosomes, if it is not being updated continuously, then we stop. Okay, this is the criteria that okay, we are no longer able to get a better value. Okay, so that will be our stopping criteria. And in this one, basically, whatever the initial population you have created, let's say you keep the entire population same. So let's say there is 100 population size, and if I randomly pick 100 means I'm going to pick all of them. So it is no longer random. Once we pick everything, like all the 100 chromosomes, it will look for the best. So whoever has the highest fitness will be the best. So that will be chosen as a parent. Then I will again randomly pick the same 100 chromosomes. Again, the same parent will be chosen. So all the parents will have basically will be same. Once all the parents are same, when we apply the crossover, they will result in the same basically childs as well. So our entire population will becomes the clone of each other. So it's basically if you keep like entire population equals to the or like this for the tournament selection, the number of chromosome equals to the population size. The entire population will become clone of each other because the same parent will be there and it will create its own clone even if we perform the crossover. So once the own clone is being created, whatever is the initial best solution, we will end up with that solution itself. Let's say in crossover, in mutation, if we change something, and if that becomes the better solution, so it's a completely like random search. That if mutation is able to move the entire solution away, then only we can hope that our we will get new solution. Otherwise the entire population will be cloned. So it is best to keep this value, so it should not be kept equals to population size. It should, I would prefer, 2 or 3 only. Okay, let's say if there is 100 population, and if I take 10 random so instead of like keeping all 100 as a population size NT value, let's say if I pick that I will choose 10 random chromosomes to check or basically to play the tournament with. So I will play select 10 random one, and it's most likely that few of them are basically repeated. Okay, so the entire population will again move keep on selecting the same parent. So it's most likely that if as this NT value is growing or basically increasing, the chance of getting same parent multiple times in the tournament is become high, and that creates the chance of cloning as well. Okay, so keep this value as low as possible. Usually like 2 and 3 we keep, so like only selecting 2 chromosome, and we'll compare them, and whatever is the best we will use, or 3 chromosome at least. Okay, so this is the tournament selection. So There are other methods as well, but these are like the classical one: roulette wheel, rank method, and tournament method. Once we have obtained these one, we perform the crossover. Okay. So, we have used certain selection methods, and you basically obtained certain parents. Then we use a crossover. In crossover, we have some crossover probability. Okay. So again, it's a randomness. So we will randomly generate a value between 0 and 1. If this randomly generated value is, let's say, less than the crossover probability, we will do the crossover. Okay. So if this is less than the this value, perform crossover. If this randomly generated value is more than our PC value, then we uh, do do not crossover. Okay. So let's say I have two parents, okay, which has been selected from the there are three methods: roulette wheel, rank, and let's say the tournament method. So we have uh, come up with two parents. Then we will randomly generate a value. So once the two parents has been identified from the selection method, we will randomly generate a value and see whether it is less than this crossover probability. We will do the crossover. Otherwise, those chromosomes will go into the next population by default. Okay. Generally, the crossover probabilities are considered like 0.6 to 0.9%, like very high probability, and we want the GA to perform crossover, so that the best features can be exchanged. Okay. Uh, how we will do crossover? Let's discuss it later on. So, so far, we are basically having certain old population. This is old population, and let's say these are sorted as well. So 2% are move forward to the new population. Okay, so it is called elite chromosomes are directly carry forwarded to the uh, next part. Then we either use, like sometimes use 80% or sometimes use 70%, or sometimes if we are using these tournament methods and roulette wheel and all, some methods are using if we are for the selection, then we basically, so I gave you, like, the very simple one. One is basically short all the population and keep certain percentage for the reproduction. So let's say there was 100 population size, and what I have done is, like, I kept 80% of the chromosome, the best fit 80% chromosome. Then randomly select any two parent chromosomes from there and do the perform the crossover. So that is one way of doing it. Another is using these other methods to select a particular parent. So we can perform this roulette wheel, rank method or tournament and identify the two parents. Is like random identification of the parents. Usually, like if we are doing any random two parents, we would prefer that at least the least fitness parent should not basically reproduce. So we like sort the population in the order of the fitness and keep the top ones. Okay. So, so let's say we are using the entire population for crossover. Okay. And applying some method. So in this one, like, selection method. Okay, so selection method will be adopted. Then after that, what we will do is, first of all, a selection method, and then two parents will be identified. Then for those two parents, we will let's say parent 1 and parent 2 has been identified after the selection process. So this, then we will again generate a random value. If it is less than the crossover probability, we will do the crossover. Okay, so we'll perform the crossover and place them here. So it is basically uh, let's say child 1 and child 2. If this random value is more than crossover, we will place the parent 1 and parent 2. We will copy them as well in the new population. Okay, so this is how we perform the crossover, and we will do this until the uh, entire population has been created, the same population. If you have any doubts, you can ask me right now. So what is the impact of crossover probability, how the selection is done, and how we perform the crossover? We will talk about them and that later. But let's say some crossover we will perform, and after the crossover, we will basically create two childs, and those childs will join the new population. So what will happen? Okay, my question is, what will happen if this crossover probability is 0? Anybody? If PC is 0, what will happen? Yes, thank you, Satya. So you can see here that out of the entire population, we will apply certain selection method and identify the two parents. Selection methods can be like, the very simple one, randomly selecting any two chromosomes using roulette wheel, or using rank method, or using tournament method. So those methods will be applied. Once two parents has been identified, if PC is 0, if you generate any random value, that will be always greater than 0. So you will end up with the second case, that R is greater than PC, and whatever is the population, it will be copied paste to the next part. Okay, so what we are doing is the best chromosomes out of this will move forward to the child, and there is no crossover between them. Still, the worst one, like whoever the chromosomes on the bottom, because of the selection methods or the pressure of the selection, they will not be forwarded to the next part. Only the um, better, like if we are applying certain tournament method, the out of two, only one will be the parent. So the worst chromosome can never move, move come from the this particular like old population to the new population because of the selection method. So selection method will be there in between. So this PC, it means no crossover, and if no crossover is there, we are not basically exploring the local search. We are not doing. We are just dependent upon the like keep on the rotating the same, or basically keep the same uh, population. So we are not creating a new population, but in every iteration, uh, the best chromosomes will basically pass on to the next one. So let's say if we do not perform mutation here, uh, in the it's again hypothetical. It will depends like how these random values between in the selection process are working. So some random parents will be selected, and out of those parents, so those parents are basically superior to others. That's why they are basically they will have higher chance of getting selected. And so in the first iteration, we will basically discard the worst solution. Okay, and move forward to the whatever the initial solution, initial population that will be carry forwarded over time, but at the end only the best solution will be there. So it is just like I gave you this tournament selection where everything was like in the one iteration itself, the entire population will become the clone of the topmost initial uh, chromosome. Here, the same cloning will happen, but in some iterations, because we are doing the selection process. So few of the chromosomes will be left in the one iteration, then some will be gone in the second iteration, and like in 3-4 iterations, the entire basically our population will be clone of each other. Again, same thing. So this species should not be very low. So it should not be. Okay, so our crossover probability should be very high. So that's why generally we keep it like more than 50%. So 62 and it goes up to 90%. That at least, like whenever we generate a random value, it will be selected. So if 90%, so it's a 90% chance that we are going to perform crossover. Okay. So now let's say this new population has been created. So the old population was of 100, let's say 100 size. Now the new population will also be of 100 size. Once the new population has been created, we will perform the mutation. So I don't know what is the topic number. Okay, so then we will perform the mutation. So it is mutation is again some mutation probability will be considered, and it is very small. Okay, usually less than 1% or equals to 1%. So let's say if I consider mutation probability equals to 1 for this particular population. So 100 population is there. Out of 100 population, I will mutate 1 bit or 2 bits depending upon like how much mutation I want. So usually it should be very small. I will change 1 bit, flip the bit, like instead of 0 I will make it 1 or 1 to 0. So first of all I will select a chromosome out of the new population, and let's say the probability is the percentage I'm keeping is 1%. So I will perform the mutation, let's say on the 1%. And once 1% is uh, there are again different ways of looking at the problem. Sometimes like we call this probability like like 1%. So we will perform mutation on 1% of the entire population. Sometimes we perform mutation over entire population. It's not up to 1%, but we will again generate a random value for so we will for each. Okay, let me write it down like this. For each chromosome, generate a random value. If that random value is less than and equals to the mutation probability, perform mutation. Okay, mutations are very rare, so that's why. Otherwise, if R is more than a PM, do nothing. Okay, do not perform the mutation. Usually, like if this is less than 1%, it's a very low chance that the random value is less than 1%, because it has a scope 1 to 99. Okay, so out of 100 we will hardly mutate 1 or 2 chromosomes. Okay, because 100 probability is there, and if I assume that every time I will get the unique probability. So let's say point 0.1, point 2, so like 1%, 2%, 3% out of 100%. Only one time it will be less than and equals to 1%. So I will perform mutation on the only one chromosome. For whichever chromosome this random value generated is, if it is less than the mutation probability. Usually it is less than the 0.1 as well. So there is a question: for all the process of GA like selection, crossover, mutation, a chance is taken which is in term of a probability. Yes. So selection as well, we are considering a random value. We are generating a random value. So it's again rolling a dice. That's it. Okay. Then for performing, so far we have discussed, like, elitism is directly 2%. So let's say if there are 2% population needs to be elite, we will forward the 2 chance. So there is no chance in the elitism. Now selection is chance based. So we have discussed, like one is random selection. So I can call it random selection. In this one, we are basically sorting all the population with the fitness, and then keep, let's say, 70 or 80% of the total fitness and randomly select 2 parents. So again, we are doing randomly. In roulette wheel as well, we are keeping the entire population, okay, but we are calculating the probability and randomly generating a value which will basically lie on this wheel, and based upon that value, that will be selected as a parent. Similarly, we have to identify 2 parents. So it's a very high, or basically, like, everything is random. So roulette wheel rank a tournament. Once it has been done, we will basically check whether we want to perform crossover or not. So that is also based upon a certain, like, randomness. Okay. So it's again up to the chance whether we are going to perform crossover or mutation, crossover as well as for the mutation as well. Okay. So once mutation has been done, we will repeat the same process. So again, go back to the decode part. Okay. So we will add. So once the new population has been created, we will again decode that population and check for the limits again. So, like, we will go back, decode the chromosomes, obtain the real values, check for the limits. If the limits are in the range, we will obtain the fitness. If the limits are not in the range, we can adopt either of these 2 methods, either keep it to that particular violated limit or keep the fitness 0. That fitness 0 is basically, like, discard that chromosome completely and out of the selection. So like if it fitness is 0, let's say I'm selecting random selection as well. So those will always, like, the 0 fitness chromosome will go out of the randomly selected, because we are sorting them with the highest to lowest. Roulette wheel, the probability of that particular chromosome will always be 0, so it will never be selected as a parent in rank as well, and in tournament as well, because the fitness of that particular chromosome is 0. Okay. So sorry. Then we perform crossover mutation and so on. So this is the entire genetic algorithm, or very fundamental genetic algorithm we can do. There are multiple methods or multiple ways of looking, this entire problem. One is like another ways of, like doing it. So it's again a logical part. So there is no standard that, okay, if I'm using some or adopting some procedure, whether like I have to follow the each and every steps as I explained to you. No, there are multiple ways of doing the GA, but the overall crux is some random population creation, then decode that and obtain the fitness. How you obtain the fitness? It's you can apply your own logic. Like, I have given that whenever some constant violation is there, I will use a zero fitness to that particular chromosome. So that fitness evaluation is there, and then you can apply your own logic how you want to obtain the fitness. Once fitness is there, there is different methods for selection, and you can apply different techniques there as well. Then crossover methods, they are also very different. Lot of crossover methods are there. Uh, so you have to look at the problem, nature of the problem as well. Okay, that will and you have to apply your own logic that okay, which method is will give me good solution. Then once we have done that, the third part will be like the mutation. And okay, let me tell you like one another approach which I have used as well. So sometimes instead of following this entire process, what I do is I move these lead chromosome to the next process or next. Um, my voice is audible. Why this message is coming? So let's say 2 to 5% are basically moved here directly. So that is elitism. Like elite chromosome has been moved. Then the bottom, very low fitness, and let's say 10%. Sometimes I do mutation over them and keep them here. Okay, but this mutation is not very small. I randomly change everything here. Like just look for the different solutions. So instead of slightly changing a very small bit flip, I perform a serious mutation there. Okay, so instead of single bit flipping, I flip multiple bits so that some random. So basically, I'm creating a random population every time by using this kind of thing. So it will have the new population, and I can say this is a random new population. Okay, because and mutation is like I would call it like highly like high degree of mutation. Instead of very small change, I insert a very large change in the bottom fitness. So this will keep on like randomly creating new population. Will keep on looking for global solution. Okay, there is a chance that okay, initially what I'm getting was not close to the global optimal point. So I will keep on exploring the new areas by creating the new population with a high degree of mutation. Then another is um, and there is a chance that this new population will have better solution. Another is applying crossover here, and this will be like child, and both of these are parents, so child population. I adopted this approach as well. For few of my problems I adopted that I will keep on looking for the global optimal solution, and I will perform, and in the next iteration a few of the newly created population will basically move up. So few of them may move up, and a few of basically these will move to the bottom of the our ladder. Any doubts if you have? I am open to questions. You can ask me. We will talk about different variants, Yagna. Yanga, we will talk about, there are different variants, fuzzy, adaptive, real coded, robust, different variants are there. Okay. I can easily take 10 to 15 hours on GA. There are so many variants. Even like this one, I have not read it somewhere, like the method which I like explained, like this is how my take on GA. So I usually keep this kind of approach as well. So you can adopt your own approach. If this problem is very non-linear and non-convex, I prefer this approach. Okay, maybe it is available in some of the paper, maybe it is not, because but I can use this kind of approach as well. Now let's talk about. So it's a very different approach. Now let's go back and see how the crossover and mutation is performed. So let's say we have generated a random value that is less than our uh, crossover probability. So we will perform the crossover. So the crossover can be, of multiple types as well. So it's like, single point, multiple point. So these are like few two methods. There are many basically again. Okay. So what we do is we have a parent one. Let's say parent one. Then we have a parent two. And if we are using a single point, so this will be the size of like a size of chromosome is in this particular direction. So this is the entire size of the chromosome. Between the size of chromosome, I will randomly, like, the size will be between 0 to uh, this size. I will randomly create a random value and put a vertical bar there. And then we will switch the values. So this is called single point crossover, that I will move this part here and move this particular part here. So we will get two, let's say this is 0, let's say this is X, and this is, let's say, size. So that after doing this, we will get the P1 from 0 to X will be here, and then P2 from X to the overall size of the uh, chromosome will move here. So this will be the child one, and another is like P2 0 to X will be here, and then P1 X to the size will come on this particular part, and this will become the child 2. So this is one way of doing it. 2-point crossover, we will keep two chromosomes. Okay, so this is let's say red. This is, let's say, P2, and another one is P1. Then we will perform a 2-point crossover. So I will insert two random bars. Okay, so two random positions from where we want to perform the crossover. And in this particular case, the child will become, like this one. Then this one, and then the red one. Okay, so we will twist them and move basically. So between the 2 points, we will shuffle. So the second part will also be like, the red part will come here. So like the portion of the parent one will be here, and then we will have the parent two's portion, and this is how we can produce the child one and two. So this is what we can do. Any doubts in this particular part? Thank you. Sometimes both of these 1 point and 2 point crossovers may create problems, and like update in the variables will be very less. And let me tell you how and why. So if we look at our initial economic load dispatch problem, the chromosome CH1 was 10, 10, 10, 10, 10, and 10 bits. So it was 60 by 1 dimension was there. Similarly, the child 2 will also have, this 20, this 20, and this 20, and 60 by 1. So, sorry, one parent, let's say the P1 is this, and P2 is this. So, this is P1 and this is P2. Okay. If I use a single point crossover, I will, let's say, randomly divide it here. Okay. So, it means the child 1 will have same P1 value, P2 value will change, and same P3 value, because this is P1, this is P2, and this is P3. Child 2 will also have same P1 and P3 values, and only P2 value is going to change. Okay, which we don't want. We want that all of these values should vary. Okay, so that we get a better solution with the particular problem. So sometimes we want that, sometimes we do not, and so that's why you can have multi-point crossover as well. For economic load dispatch, gradient is the best. You don't need a GA for that. Okay, GA is not good for economic load dispatch. It is like, simply we can take derivative. There is no non-linearity. So we should not use a genetic algorithm for the economic load dispatch problem. It's a very simple problem. Okay, until unless there are multiple objectives, there are discrete variables where we cannot take uh, derivative. Okay, so if there are discrete variables, definitely we should go for the nature inspired algorithm, whether GAPS and all, and we should not go for the. So if it is differentiable, if the solution space is convex, we should never go for the nature inspired algorithm, because the conventional methods will give us the better results. But if the solution space is not convex and concave, then they will definitely not give you the solution. So we should apply for, or go for the our nature inspired algorithm. Okay. So this is like, instead of like doing this, what I would have done is, let's say P1 and P2. So this is parent 1. This P1 we are confusing with the PG1. This is parent 2. This is also parent 1 and parent 2. So there are 20 bits here, 20 bits here, and 20 bits here. Okay. So here, instead of like one crossover, we should perform multiple crossovers with each variable, because the variable size, basically the number of bits the variable is taking, is too much high. So we should perform the crossover with respect to each variable. Okay, so this is the better way, better way of doing it, but it's again depends upon the the problem's nature. Sometimes like some binary variables are there, so they will always have 0 and 1 or some integer values. In that case, uh, performing for each variable is not logical, so we have to perform on the entire string of the variables and just move certain, shuffle certain bits, so that we get end up with the particular different solution. But for this economic load dispatch problem, I would prefer that we should basically do the crossover for the each variable, and we'll get a different new values with the each chromosome. So then we will obtain new childs, and we will look for their particular values. Here, any doubts if you have? I'm happy to answer them if you have any doubts. No doubts. So there is one important thing. It's whatever I have explained you are some very fundamentals about the genetic algorithm. Okay, I would recommend you use these AI tools, like this Chat GPT, or this Perplexity, and different chatbots are there. So use them, ask them different questions, like what are can be the different methods for, instead of roulette wheel, how can I produce random values, and everything is basically available there. So what are the different crossover methods? So one point crossover is there, multi-point crossover is there, then some uniform crossover is there, sometimes reduce surrogate crossover. Lots of ways are there to perform crossover as well. We only discuss 1 point and 2 point, but there are a lot of ways of doing the crossover. Then sometimes we perform, we want certain segment to be copied pasted, and only perform the crossover on the certain part. So some ordered crossover can also be done depending upon the the very complex problems. We have different crossover methods, and you just keep on looking for different methods. It is available on the our AI tools with the, and you can apply them here. Some fuzzy methods are there. Real coded parameters can also be basically performed, like we can perform the crossover on real values as well. Okay, so sometimes instead of two parents, three parents are needed. Okay, so some three parents are needed, and randomly we are basically creating three childs or two childs out of the three parents. So that is also possible. Sometimes only one basically parent is needed, and we swap the digits in the one single parent. Single parent crossover is also possible. Like just keep like that traveling salesman problem where a sequence of cities has to be identified for a traveling salesman so that the cost that distance he is traveling is minimized. In that case, the each bit represents each city, and whether it is linear with the sequence, it provides a particular sequence that okay, in this sequence, he should go to those cities. So we can switch the cities. Okay, we just switch the cities and check whether the but new next solution is better, right, good or bad. Okay, so we can with a single parent we can perform the crossover as well in that particular situation. We can have those standard 1 point and 2 point crossover as well, but we can perform the single point as well. And so different methods are there. I would recommend you go through extensive search. Just keep asking multiple questions to these like chat gpt type of tools, and they will give you different ways of performing crossover, performing selection, and performing mutation as well. Okay, so if you have doubts, you can put them in the chat box, and otherwise we will end this particular session. So tomorrow, I think we have a class, and the timings will be 1 and 2 to 4. So we will follow the same 10 to 11 class. Okay. So thank you. Thank you very much.